Everybody, do you hear me? So everything's okay. Well, I think we'll wait about 2 or 3 minutes, and then we will start. So if you have some questions about the previous work, on the previous maybe homework, so you can ask me now. Well, so if you want. So let's start. Today, so first of all, I show screen, and I really hope it's all okay. Maybe I just reconnect because I allowed right now in my settings, so in my preference, to share my screen. So and I have to reopen Zoom. Great. So I'm here. Do you hear me? Please tell me if not.
Yes.
Yes.
Yeah, great. So thank you. So now you have to see my screen. Well, do you see my screen? So okay. So today okay. So today I'm just provide so manage this seminar from my workplace, from the office. So and I use that's all. That's why I use my work laptop. So, but I think nothing will change. So you can see my screen. I hope. Yes, is it right? So you can see the lecture slides, I mean, and Google Colab. So am I right? I really hope yes, because okay, you see it. That's the question. Yes. Yes, I
Yes.
will. Okay, so fine. Thank you. So today's lesson will be about model 3 learning in reinforcement learning. So, but I will I will tell you something about more preferable for about co-learning. So co-learning is one of the methods of reinforcement learning. So and we will see how it works. How it works just in logical, like in theory, yes, in formals. We just briefly discuss the lecture. So then we will move to the practice. So and we will solve some two tasks just in code. So first task will be code ball. So I think you remember about it. So but maybe so we will see how it works, how it learned. So and then there are other tasks about taxi. So let's start. This is some briefly outline. So about our just a brief theory lecture. So yes, we have some recap. Then we will discuss about value function and co-function. Yes, about reward discounting and cumulative reward. What is it and why it's so specific to choose it. Yes, then we will move to co-learning. Yes, and then temporal difference, and maybe we will touch some approximate co-learning. So let's start. Here are some references. This is the main, main start, yes, starting point. So about how we can find an optimal policy. So as you can see, we have some definitions of Markov's decision process, yes. So we briefly discussed in our previous seminars, yes, just 2 seminars ago. But overall, Markov decision process or MDP, yes, we have our tuple about our set of states involved. We have some set of actions, yes. Then we have our transition function, yes. It's which can provide our new state based on the previous state and action. So the next state. So yes, and our reward function. Reward function is giving just a value about reward based on the state and action. So and Markov property, yes, it's the main decision, the main idea. So our next state expects reward all these. I think yes, this tuple depends on previous state and previous action. So so we have some chain of our states, set of actions. Yes, of course, reward, some state transition, and there we can use our transition function. So this is the idea. This is the main idea of MDP. Yes, and how we can find the optimal policy. Yes, so what is objective? Yes, what we can use, what we can just set something. Yes, so it is 2 values. So first of all, it's reward. Yes, discounting and design. We can design a reward function. Yes, and expected objective, of course, it's the state and action function. Yes, action value, state value functions. So, and we will start with the reward function and reward hypothesis. So this is Sutton reward hypothesis. Yes, goals and purposes can be thought of a maximization of the expected value of the cumulative sum, the received scalar signal. So we have some our cumulative reward. We will call it like a return, but sometimes it's like a J. So this is the things like, I don't know why this J, why don't CR or return or R? Yes, okay, of course, anywhere. So we have these cumulative reward, the sum of our rewards, yes, and we have like immediate rewards, so many for each steps, yes, and of the episode. We can sum it, yes, make a cumulative reward, and so then it can return. So reward, for example, reward in chess, it's a value of taking opponent's piece, yes. But of course, we can understand that something can be wrong with reward. So because it's a really hard task to implement or to generate the really correct and accurate reward function. So, for example, so we have our data center non-stop cooling system. Yes. So states is the temperature measurements. Yes, we have just 20 degrees or 15 degrees or 40 degrees overall. Yes, our actions. It's a different fans speed. Of course, we can fans like I don't know, like 1000. Yes, so the speed, yes, or something, yes, or 2000, something else, yes. And want to, if we exceed temperature threshold, yes, just our reward is 0. If we, for each second, system is cool, yes, our reward is +1. Just everything is okay. So what can be wrong with such design, with this design function? Yes, so if we in infinite summarize our rewards when our system is cool, our system not exceed temperature thresholds, so we return infinite value. So we have non-optimal behavior is 0, but overall in the sum with some yes, just one values, so many values because it's of each second. So we have our time axis, yes. So and as a result, the value, the final return will be infinite, and we couldn't manage infinite. So here, so that's why it's wrong with this reward function, reward strategy, I think. Yes, and one more example about cleaning robot. So we have our states. I think some dust sensors or air sensor, yes, or lidar or something else, yes. Of course, we have our actions. Cleaning action, rest, and conditioning, yes, air conditioning, just on or off. So rest, it's like your cleaning robot is on the base, yes, and everything's good. So and we'll choose the reward strategy, just reward 100 for a long, tedious floor cleaning task done. Yes, great. But and reward 1 for turning air conditioning on and off. It's a simple action, yes, just turn it on, turn it off. Okay, now, based on this example, I think you have now some intuition, yes, about how can the what can be wrong with what function. So you so tell me what could go wrong with such design, with this design reward strategy, if our episode ends each day. So any thoughts, any just opinions about it? It can be some just intuition if you have. So you can write down in chat, and okay, I will name one of you. So to answer the question. So I'm sorry if I will wrong with your first and last name. So Fernando Paruri, please, could you tell me some opinions or thoughts about what can be wrong with this reward strategy if we use our cleaning robot each day? And we have episode each day, so and we have just 100 reward for a long tedious floor cleaning task done, yes, and turning air condition on and off. So what can go wrong in this strategy? Any thoughts, maybe your opinion?
I mean, the reward system here is pretty strange because the robot could just choose to do like single task, like easier task over and over again, and like may have higher returns overall at the end of the episode. But like even though the reward is high, the actions are not optimal because it's not doing the long, tedious floor cleaning tasks.
Yes, you're quite right. So thank you so much. Um, the main uh, the main error of this incorrect behavior of this reward strategy is that our robot or clean robot can do some simple and of course short in time tasks. Yes, in reward one with value one for turning air condition on or off. Uh, and okay, it can receive the reward 100 for a long tedious floor cleaning. Yes, of course it's done, but we understand so that turning air condition in per second, 1 second on and off. Yes, we in 100 seconds, it's less than 2 minutes. Robot can receive the equal reward as for a long tedious floor cleaning, which can, I don't know, just how, this clean can be about 15 minutes, yes, or 20 minutes if you have cleaning robot in your room, so you know that cleaning all flat or a robot, yes, it's uh, it's not just a quickly task. Yes, of course, it's some hard work for them, and they, I don't know, just which can produce just during 30 minutes. Yes, but in here, robot just can turn air conditioning and great. That's all. Yes, so this is the wrong um, wrong term of this strategy. So, and I want to show you some OpenAI blog post about filter rewards, so we can hear it, we can see it here. So yes, this is the task was just to make to go with a bot, yes, to just manage with this bot, control it, yes, and to make some extra pluses boxes, yes, for additional scores, yes, and then we have uh, final our route, yes, and our route. And here you can see the not correct behavior of your agent. So the agent have this box, yes, and so we have the researchers, so they um, did the strategy, so to launch the strategy of this bot, so to receive these additional bonuses value boxes, yes, but this went wrong because as you can see, bot will find will find some special place as in a trace in in a race. So, and then it begins just in a loop, going in a loop in this place. Even it damaged itself by other boats or by walls. He received a lot uh, values, a lot reward of this task, and this is of course not this is not the expected behavior of the rule, yes, of the game, of the researchers, of course, but it's so you can read here that in so this agent achieves average on average 20% higher the average score is the average reward than achieved by human players just on this loop. Yes, this is not expected behavior, and this is the bad reward function, the structure, bad what's function structure. So, and this is why reward function, reward strategy is matter. So it's matter a lot in reinforcement learning. So, and you have to understand the correct reward function. So what we can do this with reward function, yes, for example, oh, here you can see, yes, in 1 second, yes, the whole day. So this is positive feedback loop. Yes, we can see this is the same problem what OpenAI blog just they wrote down. So in it. So, and now I want to underscore that we have some special strategies of reward function. First, this strategy is reward discounting. So this is we, of course, as you can see, we sum our cumulative reward in a J, yes, in a big J. So we sum our reward in each step, yes, and we can discount it by some value from 0 to 1, yes, to avoid the infinite sum, yes, and overall, yes, as a result, we have some threshold, yes, of some not infinite value of reward function, yes, as a result. And for example, you can manage this discounting too. So first of all, you can do it just in an example of cake. Yes, if so first gamma 1, yes, just without some power. So gamma will eat it day by day. Yes, for example, some cake. And gamma 2, that's like less than tomorrow, and then sometimes less than day after. Yes, etc. So this is how we create a reward. So if our cake is not really good, so sometimes people can eat it times less than day after. Yes, and this is the so our model, our agent have to receive less reward, much less. So then if people just eat it times less tomorrow. So this is the reward discounting. I think the idea is pretty simple. So yes, and now we move to discounting. We just finished it. It's the reward function, yes, but I want to show you that in these series we can use this formula, yes, in this formula we can choose our values of the gamma. Gamma is the hyperparameter, yes, we can set it, and for example, as you can see in this graph, our reward value will decrease, yes, depending on gamma. So, and of course our steps. I think it's pretty simple. So if the larger your gamma is, yes, the larger just, I mean, near the 1 value, yes, the quickly, quickly, so your reward value will decrease. So, okay, so and of course this is the rule. So if you use discounting changes in your reward strategy, your optimization task and of course the solution will change. It's the rule. So and of course you can understand that the values of reward will change. So now we finish with our reward, reward function, reward strategies, and we'll um, talk with you about state and action value functions. So state value function, what is it? So we just set it like VS, yes. So NVS, this is the state value function. This is expected return conditional on state. Based on state, this is it's vital. Yes, so as you can see, we expect our return, yes, our sum of our rewards, yes, based on state, on the current state, for example, yes. And as you can see, we can manage our function, yes, and by definition, so we create this. So as you can see, the main reason why we can use state value function, this is that the current value function depends on the previous value function. As you can see here, here's the proof. Yes, so we create our formulas. Yes, we just can separate our policy. Yes, and here you can see this is the same, but in the next. Yes, so in the next. So this is the rule. Okay, great. So and we can we can value the following policy from the state S, so we can make it the state value function. So yes, and the action value function, as you can see, this is pretty the same, but we base on our state and action. So here we base only on state, as you can see. So our next state, yes, and we create our formula, yes. Okay, great. But here we can use not only state, but action too. So, and this is expected return too. So we just take this expected return, this expected return on the cumulative reward. So, but here we base on state, here we base on state and action. So, and we just set it like Q. Q depends on the policy, yes, and this is we can make the same rule as the previous, yes, this definition, the previous just managed with formulas, yes, and here we can see so our action value function depends on the state value function, yes, on the next state, yes. So this is our intuition, yes, is here. This is the action value is a value of the following policy after committing action A and state S. This is, we can just use it, yes, it's just to see, to test the future, yes, test the future results. Test the future results if we will use our actions, yes, or our states, something else. So, and of course, we have our relations between value function, yes, and action function, state function and action function. So we have some formulas, so and now we can see, so it's depending about our PS and QS, yes. So this is the formula, this is the tricks, some formula tricks, you can see it in the lecture, so we have a seminar, I remember you, yes. Yeah, so it's pretty simple tricks with formula. Yes, we just see something, yes, we just manage it, and then we can make the final result. But pay attention to the lectures, because this is the idea. We just have a brief example, some talks about the lecture, the previous lecture, yes, following to the seminar practice. Yes, so this is the Bellman expectation. Yes, okay. So it's for our action value function. Yes, and here to sum up. Yes, to sum up at the really vital slide. Yes, so value value function value function. Yes, we expected our cumulative reward G from the state if we follow P. The optimal value function is with a star. Yes, V star. It's expected cumulative reward from the state S. Yes, if we follow the optimal policy. Optimal policy usually it's set as a P star. So in our active function, yes, it's P expected cumulative reward from state S if we start by taking action A and follow P policy from the next state. Yes, and of course the optimal is the same, but where we have optimal policy, and this is the final formula of Q star. Yes. So and so now I want to make you about to tell you about some model-based, model-free methods. Yes, and learn from the trajectories. So trajectories, it's just a simple idea. If we have our previous state, previous action, now we have current state and current action. We have some reward. Yes, and then we have the next station, next action, next state, next action, next word, and something else. Yes, so and model based, if we know our it's the probability of the next station based on our current station and current action. And we of course apply some dynamic programming, so and we can plan our actions. Model free, if we can sample trajectories. So, and we can try to stuff out, yes, and we can just manage it or some choose the best, yes, but insurance not included, of course not, because we just sample trajectories, yes. This is the base differences between model-based, yes, and model-free. Model-based is because we have this probability, model-free because we don't have this probability, and we have to sample trajectories, yes, and then choose the best one. So, and here the example, yes, so we have our states, actions, rewards, and we can only sample trajectories. So, and what we can learn, so of course, value function, yes, or our Q function. So, but value function is useless without our knowledges, yes, without our probability of the next station based on our current station and current action. That is why we can use some ideas, yes. First of all, Monte Carlo, yes, of course we can choose, get all trajectories we containing our particular state and action, then we estimate our reward for each trajectory, and then we average them to get expectation. That's all. So we can just produce something, yes, something new, and then we just have the one trajectory, yes, trajectory of our policy, for example, yes, to make a cake. Then second idea is that we can the temporal differences. Yes, first of all, a Q function can be improved iteratively. And this is what we will use in our practice part. So we have, for example, if we can evaluate from the P star, yes, optimal policy, and then we can evaluate our Q function optimal value. Yes, but we have something wrong, or we couldn't have, yes, this estimation of reward, yes, on the based on the current reward and based on the next state. That's the problem, and here we can improve iteratively, yes, because we can here we can have some formal tricks, yes, and then we just add the same, as you can see, yes, we just added the same, and now we can improve it just here, and this is what we will use. So alpha, it's the learning rate, of course, gamma is discounting, reward, maximum is we try to get the optimal policy. Yes, this is discounting on the previous states. This is the next state. So, okay. So, or you can use our coloring, and this is two. We will try to. So this is the my preferable strategy. Yes, if we generate the possible actions, yes, we just sample our states, we sample our actions, yes, from our environment on the one point, yes, and we compute new co-function estimation, yes, our some estimation, and then we update with the highest, so with the based on the maximum, yes, based on maximum function value. So this is co-learning. So this is co-learning, just the method. So we will try it in our seminar. So and as you can see here, we can some differences. Yes, because Monte Carlo we average Q over sample path, but here in the temporal difference, yes, we use a recurrent formula for Q, and we can generate like possible actions. So this is great, and this is the final formulas for Q learning formula. So I think it's pretty similar at the previous ones, but I will tell that here we try to make our optimal Q value, yes, based on the next station, based on the next action. Here our previous Q learning based on the current station, the current action. Then we have our learning rate. Yes, we have our discounting. This is reward. This is reward too. So and then we update our Q function. Yes, and the policy is maximum the argmax, yes, the maximization by our arguments is the A, because only actions we can manage, yes, only actions we can vary from our agent, yes, in our policy with we want to maximize the Q function based on our actions. So, and here is some theory adaptation. Yes, here some exploitation trade-off. As you remember, we touched with this topic in some previous seminars, but I will here want to see our mathematical improvement, this mathematical prooffulness of this exploitation trade-off. This trade-off is just you have to choose your exploitate as the current strategy, and you don't explore anything else. You don't explore the environment or something else, yes. Or you can explore the environment, explore the state and the actions, yes, set of the actions, but of course exploration can minimize or so it can decrease your cumulative reward, because of course this is something new, and so some learning something new, it's of course you decreasing your reward. So in contrast, you can exploitation your usual strategy, yes, and have the general reward, yes, and that's okay. So this is the problem, as you can see in OpenAI blog. So, and here we can some strategies. Yes, this is epsilon greedy strategy with the probability epsilon. This is the not really high probability. You can take a random action, and then you otherwise take the optimal action. Yes, you can in some other probabilities. Yes, and you can take the random action, and so this is the exploration strategy. Yes, you choose the random action, not optimal, but random from the set of your actions, and then you see how vary the state, how vary your reward, etc., and something else. Because if you choose a random action, which can be more preferable or better than optimal action in this step, maybe you can make your strategy better. Yes, and in a math language, it's just we make it like a softmax. Yes, we pick action like proportional to softmax and shift it to normalized q-values. That's all. Yes. So and here we can make our continuous. Yes, for now states and actions, they all were discrete, but if states are not, for example, you have to clean a robot or something else. Yes, you want to minimize the loss, which given the state, action, reward, and the next state. Yes, this is something like this. Yes, and you want to minimize it. You can make the formula trick, of course, because Q true, Q optimal is the maximization of the Q, yes, based on the next state and next action, yes, and here so that's the trick. So since here is MDP, some environment, yes, it's definitions of recurrent relations, yes, some your cumulative reward, your Q-function policy, value function policy, so that's all. So, and optimal policy, optimal equation, of course, it's something vital formula. So, and here you can see the training step of good learning. Yes, you can see, so we have our reward, discounting reward based on the maximum Q-value. We just decrease it by current Q-value, yes, then we have our learning rate and reward, current reward, and then we have our current Q-value, and then we update. So this is the MSE minimization, yes, if you have our const, yes, of this, and then we try to make our derivatives. So but it's wrong because sometimes it's the const of cost. We couldn't use it just derivative. So this is some example of the real world, but we will move to approximate co-learning because it's because with this theory we will try to try in our practice seminar. Yes, and this is the continuous control of the large number of actions. Yes, if we have some states and one action, we have our network, and then we generate a q-value. Yes, we can predict. So here we can given some states, we predict all q-values based on all actions, yes, and then we can generate some the most, I think, the optimal q-value, yes, and the optimal strategy. But in the approximate co-learning, so this is how it's used. So, for example, we generate all q-values based on all actions, yes, and but here we have the constant value of this, yes, and but here we can have to update our weights by our loss and by our weights, yes, and approximate co-learning, this is how we can use it. Yes, we just use our co-learning, but we have some expected value bars by SARSA, yes, by some methods, yes, and here we can use our expected value of co-learning, so based on the next step and the next action. So, and that's the final, yes, and now if you have some questions about co-learning and approximate co-learning is like when you generate all your q-values based on all actions, yes, so you can ask me now, and I think now we have to see our practice part based on our Google Colab. So 3, 2, 1. So if you have no questions, so great, and we will move to our practice. So first of all, we will start. I'm sorry, so my Colab So it fell down. So, but of course we will see the result. So this is our co-learning agent. Yes, our task is to make the co-learning agent. Yes, and then to make our tests belong it. Yes, we will test it. So and so what we can see, so we have some get legal actions. Yes, it's if we what actions we can do if we have some our state. Yes, we have alpha. Alpha is our learning rate. Epsilon it's the gradient. This is the exploration probability. Yes, and our discount our reward cumulative reward. So get Q value, I think it's simple. Based on our state and action, we can move to our Q values function. Yes. So and here it is. Here it is. I'm sorry. So this is the set Q value. Yes, this it is. So this is the value based on our state and action. We just produce our given value, but where we can use it. So we use it in here. So we just have our possible actions. Yes, and then we just get the value of it. Yes, we have just possible actions. It's when we use our all legal action based on this state. Yes. So and updation, it's how we can update our Q function. This is the main formula which I paid attention of it in the lecture. Yes, we have our learning rate. Yes, of course, some get value based on our state. Yes, we have learning rate 2. It's the alpha. So reward and discounting reward because by the get value on the next state. Yes, then we set Q value because we got our Q value, state and action. We set Q value, yes, of all our states and over all our actions. Yes, we will here make it here. So and the best action, of course, is we have our possible actions. And first of all, we have to choose the maximum Q-value state and action. That's all. And first of all, our best Q-value and best action we will infimum or none. And then in the loop, we just see all possible actions and we just update our best Q-value and best action. And then we will choose the maximum Q-value. So that's all. So this is a pretty simple loop, but we, of course, use, sometimes you can use this part, but I really recommend you to have this best action, best value. It's pretty simple. So, and get action is pretty simple. So because you just get all legal actions. Yes, you have your epsilon. Yes, it is the epsilon greedy strategy. If you have explore something, yes, including exploration, and that's the case. Yes, if you have our epsilon, yes, if you have it in your random 0, then epsilon you have a random choice from the possible actions. If else, you can get best action based on your state. That's all. So this is the simple structure, class structure of the Q learning agent. Yes, and now we will try it based on the taxi environment from the OpenAI gym. So you can see here our environment. So you can control your taxi. You have to take the passenger and drop it off near the house. That's all. So we just provide our learning agent based on our alpha or the learning rate, yes, by 0.5, some epsilon. As you can see, we have just a quattro of your exploration strategy. Yes, discount is the 0.99. So, and of course, we just make our legal actions by just a range of our n actions because we can got it from here. Yes, that's all. So, okay, so plain and trained. This is the pretty simple function. We just play the game, yes, and train our total reward. We accumulate our total reward, yes, based on our agent actions, agent environment steps, and update the agent states and some cool learning, so costume. And here our our rewards, yes, as you can see on the start, we have really less, much more less rewards than here in like in 200 steps, and even in some in 1000 steps, we got really great mean reward on the 7.8. So, and this is how we can train our agents, yes, and make some so make some actions and the policy. Choose the best policy. Yes. Here is card pool variant of the environment. Yes, and here we have our discretized state steps, and here we use something similar. We have our, as you can see, so we tried it in the previous seminars. Yes, our card pool environment. Yes, and here we just update our playing the game. Yes, visualize, and it's just visualization function. Yes, and as you can see, we have some observations. Yes, our couple positions near the zero. It's normal because we have to balance our couple. Yes, card velocity. We have something similar, just a normal distribution. Yes, and here the ball agent and ball velocity tip, we have the same some normal distributions like Gauss. So, and here you can see the discrete environment. Yes, here we can some digits, yes, feature digits, and we just generate the state based on our feature index, yes, in all of our states. So, and here we have, as you can see, some discrete positions. Yes, we just sorry, discretized our strategy. Yes, from the infinite strategy to describe discrete positions. So of course we have some not really great results, because if you can see, so we can discrete move our ball, but of course it works too. So so here some discrete positions, yes, we can train it, yes, but discrete policy, yes, and we, as you can see, we have our some various results, but in this, so in general, the mean reward function based on the last, I think, 100, yes, it's growth, and it's great. It's great because discrete positions in a card pool, you understand, so it's really complex task. So, but it learned, and it's great. So here your homework part, it's not solved, of course, obviously, but you can use the previous code based on your discrete positions, discrete environment, discrete learning, the agent, yes, learning the couple, and of course not discrete, just based on the taxim. You can use these co-learning agent. So for these co-learning, yes, and some examples based on these two environments, that's all. But I have another seminar. We have tried to approximate learning strategy, yes, and here we will use the same environment based on these card pool. So as you can see, here it is. So this is our similar, and this is the approximate co-learning. So as you As you remember, we generate our q-functions based on all available actions, yes, from this state. And then we just choose the maximum, choose the preferable, the optimal policy, the optimal value, yes, and then we just will try it. So our network is pretty simple. As you can see, we have our linear layers and ReLU function, activate function, yes, and say the final result if it, of course, only two neurons. This is why, because we can just move on the left side or on the right side. That's all. So we have to update our get action policy, because based on this epsilon greedy strategy, yes, we have some we have to reuse our torch tensor data, yes, and then we have to get our q-values from the network based on this state, yes, and then we just choose if we make the random action, yes, if our random value is less than epsilon, it's epsilon just we have parameter, yes, or we will choose our optimal action, yes, optimal, the maximum, yes, of course. So, and then we return it, our chosen action. Yes, here you can see some environment. We just check it, yes, and test epsilon with the expression based based on these epsilon list. Yes, we just have to test it. I think everything is okay. This notebook is great, so it's didn't fall down. So, and here we make our co-learning based on gradient descent. This is what we use in our lectures, our theory, yes. So here you can see here some current state, action, reward, and the next state, respectively. Yes, we can. This the four just parameters, and you have to gamma. It's the discount factor. Yes, and we'll use it to compute these laws based on the q-function. Yes, we just I think the hardest part is the next q-value based on the next state and the next action. Yes, and here is the output of our neural network. So and of course when we do our gradient descent, this is the hard moment. We don't propagate gradients through our neural network to make training more stable. Yes, this is the key, and this is the vital part of it. So we just use our detach method, yes, for function, which basically says like just consider the thing constant when doing backprop, because our q-function is the constant part. It's the constant value. This is why we couldn't propagate through it some gradients, because it will be 0. So I think you got it. So if you have some questions about it, you can ask me right now. We will return to our lectures. Yes, go back and just to see these formulas, to see this thing. Okay, so this is how we can compute our loss. Yes, we have some states, actions, reward, some next state, and it's done. It's like just it's done or not. Just yes. We have our predicted values based on the network, yes, and based on our states. Predicted values from actions, yes. Here we have to predict values, but we range it from all our actions. We predicted our next values. It's based on the network and the next states, yes, which we use like in the initial function, yes. Then we have to compute target q-values, and target q-values for actions. We just simplify formulas. That's all. We computed by reward and gamma next state, and this is the part of our formula, and then we update it. Yes, here is based on this. So just torch dot where method. That's all. And then we compute our squared loss. Yes, it's like, of course, we can get the mean of the predicted values minus target values. Then we in power 2. So that's all. And then we choose our mean. That's we can check some shapes. We have some asserts of it, but everything will be okay. So this is the really simple compute to the loss. So based on these functions, as you can see, the functions in lecture sometimes looks like just hard, complex, or sometimes not understandable. But in the computer, in the programming language, everything is everything is okay, everything is easy. This is the research research point, just trick. So when you see the code, you can understand something better. So, and this is the center checks. Yes, we just use it. Okay, everything is great. And here we can play the game. So we have optimizer. Yes, our Atom based on our network parameters and learning rate just 10,000. So and generate session. This is the previously simple function for generation our session for approximate cool-learning agent. So we have our train. Yes, we have our total result. So if we some video recorder, we can record it. So and we return our total results. That's all. Here we update our state and provides. That's all. Okay, we use our epsilon. As you can see, the epsilon is higher than the previous example because we have to explore all methods, and that is why. And why 0.5? Do you have some ideas why 0.5 epsilon, not 0.25, not 0.80? Just think about the set of available actions. Just think about our available states and think about exploration, exploitation strategies and our reward function. And then you can answer why our epsilon is accurately 0.5. Your thoughts and ideas or intuition, really, I want to hear it right now.
Because we need to find the balance between exploration and exploitation. So like 0.5 seems to be the most optimal value.
Why the almost optimal is 0.5? It's based on the set of the actions.
Uh, so where is this epsilon being used right now? Like for our example.
Okay, the answer is we have only two actions. So you're quite right, but we have only two actions. So imagine only left. Yes, for me it's left here. So from the left and to the right, our card pole. Yes, in our pole. This is why if we use our exploration hyperparameter less or more than 0.5, the exploration of one of these actions, for example, turning right is only right, will be preferable for the agent if for turning left. As you saw in the previous seminar, we have to normal distribution of our actions, of our turnings, yes, in our card pole. This is why we have just divide and we have make these preferable moves, yes, to right or to the left, just in equal. That is why we have to explore just right and left, right and left moves just in equal. This is why we have to explore these positions, and this is the small trick for your future. I don't know, just future work. If you will work with RL, yes. If you have just two two steps, yes, two actions, two possible actions. You have to vary exploration just in a 0.5 probability. So to explore all these actions and explore all states without any preferable. So this is some vital moment, but in one string, so it's really vital. So as you can see here, we have our training process. Yes, I don't want to restart it because it's some has some time to train. So because we have just 1,000 iterations, but overall we have just mean reward on the more than 300, and of course it's great. This part of of the code I didn't I didn't try, and I've tried it right now. Okay, great. Okay, great. So it works because I had some problems with my dependencies, yes, with Gymnasium and Shimmy. So, and it works great. So, and that is what I want to show you. For example, here we can see 9 seconds, and this is the result of our agent. It's the result of our strategy. Yes, as you can see, we have some problems with the moving right of our agent. Yes, but this this happens due to some I don't know, situation states. Yes, for example, we can range. Here we can see our epsilon. For example, we just, of course, we set it like in 0 because, of course, we want to in a test train in a test set, we want to choose only optimal actions. Yes, but if, for example, yes, for just to show you what will change if we set our epsilon 0.5, you will see. So here we do our video, and now that's all. I don't know why it's fall down, but maybe we will some understanding. So if we use it less, for example 0.1, okay, here's 8 seconds. So it's quite bad. So because we just in 10 10%, we have only 10% our random actions. So, but basically, if you want to use your reinforcement learning agent, yes, in production, of course, we have absolutely 0. So, because random actions, you will have not obvious result, especially if you work with some expensive tools, expensive robots. It is the critical chance. So that's all for today, guys. So I really appreciate you to go here and to see something. If you have any questions, you can ask me right now about reinforcement learning, about uh, co-learning, yes. So or write in the future me in the chat or in my message, so in Telegram. So that's all for today. So ask some questions. 3, 2, 1. Okay. Well, if you don't have any questions for today, for this seminar, for this theory lecture or some practice, so thank you very much for
Thanks for the lecture.
the meeting. So goodbye, have a nice day and evening.
Excuse me, will we have any homework or something like that?
You will have the homework based on this approximate co-learning. So we have some parts, but I think you have to see in the alerts chat, in the alerts channel chat, yes, about your homework. I think current homework, the deadline will be some prolong. Yes, and the current deadline is 17th April, but I think there's a lot, the huge homework, so I think you have to just make it in advance.
Okay.
So,
Okay. Thank you.
so goodbye. Yes, thank you, guys.